gravity at a different region. So what is the acceleration due to gravity? Yes, guys. What is the acceleration due to gravity of the Earth?
Zero.
Acceleration is zero due to gravity of the Earth. What is 9.8?
Value of gravity. G.
So G is what?
Gravity.
G is acceleration due to gravity, right? And if 10 meters per second square or 9.8 meters per second.
So it will be 9.8 only.
9.8 meter per second square. But that gravitational acceleration, and we will see that that acceleration is only on this surface, right? So when we go beyond this surface, then there is a change in the acceleration due to gravity. This part, we will calculate acceleration due to gravity in three regions. So we will calculate the acceleration due to gravity in three regions. And what are those regions? So let's say first we will calculate this. Let's say this is the Earth, and we will calculate the gravitational acceleration in three regions. So one would be this surface. These are the surface, right? So mass is 8 kg. Okay. And then we will calculate. So this radius is called the radius of the Earth. And let's say we put some mass in. So in second case, we calculate acceleration due to gravity at this point. So then what would be the acceleration due to gravity? And the third case would be that we calculate the acceleration due to gravity at so this is at the surface of the Earth. This is at some height. So this is at some height from the surface. And then we have this one. So let's say this is R, and this is at some depth. So at some depth from the surface. So far, you guys have understood or whatever G you were taking, and this was 9.8 meter per second square, but that was on the surface. This was on the, but now we will calculate gravitational acceleration due to gravity on each so different regions. So first, before we do this thing, let us first understand that what is so what is homogeneous, right? Homogeneous body and uniform shape, right? Okay, so what is homogeneous body and what is the uniform? So let's say we have some sphere, and it is of uniform density, right? Uniform density and homogeneous body means that all the particles which are there. So if I take this region, then whatever the particles are in there, so there would be same particles in there. If I take the patches, if I take the patches in here, same area, so same particles would be there. If I take this area, so same particles would be there. So this type of body we call the homogeneous body, right? And for a homogeneous body, the density is uniform. So density is uniform. So how do you calculate the density? This is density is represented by rho. And what is the density, guys? How do you write the density? Yes. What is that is mass upon volume, right? That is how we define the density, right? Okay, is that clear? You guys remember this now? My voice is lagging. Is my voice lagging now? So is it still lagging? Yes, is my voice lagging?
So your voice is lagging.
Why is my voice lagging? Why is it? Internet is working fine. Why? Like, okay, so is it clear now?
Yes, sir.
Good. So density is mass by volume, right? And if I am saying that the density is uniform, so whatever density I am taking at this point, that density would be equal to whatever density I am taking from here, right? So let's say that you have a bucket of water, right? Let's say you have this bucket, whatever this bucket is, and the water has some density. That is 1,000 kg per meter cube. So that is the density of water, right? Is that
Yes, sir.
clear, guys?
Yes, sir.
And let's say you take 1 cup of water from here, right? So let's say you take 1 cup of water from here. Then what would be the density of this water? It would be again 1,000 kg per m3, right? So the density of water will not change, right?
Yes, sir.
Is that clear? Yeah, so that is why we call that uniform density, right? Similarly, let's say this sphere is of uniform density. So that would be whatever mass I take divided by the total volume of that, right? So that would be mass by volume. Okay, so let's say that I calculate the volume of this. So I calculate, let's say this mass is mass of the earth, and I want to calculate the density of this thing. Radius is r, right? So this rho density, that would be mass of the earth divided by what is the volume of this sphere? What is the volume of this sphere?
4 pi r.
Yeah, so 4 by 3 pi r cube, right? That is the volume, right? Correct? Now, let's say I take a small volume here. So let's say I take this volume from here, right? So from this point to this point, the mass would be different. I'm taking some portion of mass, right? And let's say that this radius is r. So I have a small r. So let's say this is some mass and this is small r. Okay. Then what would be the density for this object? That would be whatever mass that I'm taking, right? Divided by 4 by 3 pi r cube, right? And this is again the density. So density is uniform, which means that this one and this one would be equal. Is that correct? Right? Is that correct? So is this clear, everyone? Hello, guys.
Yes, sir.
Yeah. So then if let's say this is 1 and let's say this is 2, then if these two are equal, then which means that this and this mass that I have taken, new mass, right? That would be 4 by 3 r. So 4 by 3, 4 by 3 cancel, pi cancel, and m prime, that would be r cube mass of the earth divided by this earth. So just remember this relation, that would be very useful, right? So we will use this relation at some point. Okay. Yeah. So just remember this thing, and now let us calculate the acceleration due to gravity at different regions, right? So first, let us calculate acceleration due to gravity at surface of, right. So that would be how much? Let's say this is the whole Earth, right? The mass of the Earth is me, right? And the radius that we are taking is r. This is the radius of the Earth, and some object is placed at here. This is of mass m. Okay. So we know that what would be the Newton's law of gravitation? From Newton's law of gravitation, this whole mass will contribute, right? And it will be situated at the center. So this GME and this M divided by this R square. Right, guys? This would be the force,
Yes, sir.
gravitational force. And we already know that this force would be equal to mass into acceleration. And this is facing the acceleration, let's say, that we call as g. So this would be, so this m will cancel, and this is the value of the gravitational acceleration at the surface of the earth. Okay, is this part clear?
Yes,
Yes,
sir.
sir.
Yeah. So now we can calculate the acceleration due to gravity. Let me write the shorthand notation. At some height. So again, I have this Earth, right? And the object is kept at some height. So this distance is h, and this distance is r, right? So again, this is the object, and again this whole mass of the Earth will contribute, right? So again, this whole mass of the Earth will contribute, and the gravitational force, again, that would be how much? And whole this mass would be situated at the center, right? So that would be G and ME, M divided by what? What is the distance between this object and this point? What is the distance?
H.
We take the distance from where? Surface or the center?
Yes, sir. From surface.
From surface we take because all the masses are situated at the center, right? So we take the distance from the center, right? Because this is a spherical body, spherical symmetric body, and we make it a point mass. So the all the mass would be situated at this point. So the overall figure is this one. This is because Newton's law of gravitation is applicable only for point, right?
Yes,
This
sir.
is the this is the separation between them. So this will feel the separation, not only this H. So what would be in here? Yes,
Sorry, sir.
separation. What would be in here in the denominator? What would be in here in the denominator?
H plus R.
Square, right? Separation square. So R plus H square. So this is the gravitational force. Is that clear, right? Because
Yes, sir.
gravitational force is dependent upon the product of the masses and the inverse of the separation square. Good. So now what we can do from here that we know that F is from Newton's second, right? From Newton's second law, we know that this would be m, and acceleration, and let that acceleration as gh. Gh signifies that gravitational acceleration at certain height. So this would be gm m divided by r plus h whole square. Again, this is cancelled, and if we take so if we take this r common, so if we take r common and take it outside of the square, so we'll get square, and then we'll get 1 plus h by r and power square. Right, guys? Is
Yes,
it?
sir.
Okay, so is this part clear for everyone? Clear? Why this is r square? Why this is square? So is it clear?
Yes,
Everyone?
sir.
Good. So then what we do is that we take this one in the numerator. So this would be h by r and power minus, right? And if your height is very smaller than the radius of the earth, right? Because the earth is so big. Earth's radius is 6,400 kilometers. And then let's say you are some 3 kilometers above the surface of the earth. This distance is as compared to this one is very small. So this height is very small as compared to the radius of the earth, right? The whole planet Earth. This is this, which means that we can use the binomial expansion and we can write this one as ME and R square, and this is 1, and this minus 2 will come in here. This is minus 2h by. So again, what is the binomial expansion says? So it says that if you have 1 plus x to the power n, and this x, so this x is very smaller than this 1. Then from binomial expansion, we can write this 1 plus xn as 1 plus nx. Right? So this power n is just simplified to these two terms. So when this x is very small, right? So that is what we have used. This power comes in front of this x part. So x was this, so power comes in. Minus 2 comes in. So GME by R square, what is that?
F.
GME G, that is G, right? Small g. GME by R square is small g. So GH would be G and 1 minus 2h by 1. So that is the acceleration due to gravity at some h. And we can clearly see from here that the GH will decrease when we go above the surface, right? Which means that we are subtracting this 2h by r from g, which means that this g is greater surface, your gravitational acceleration is greater than at some height. So if you go above the height, then at a certain height, then your gravitational acceleration will decrease, which means that the Earth will pull you down with a smaller acceleration. Is that clear?
Yes, sir.
Yeah. That is what we use in the escape velocity, because the Earth's power to pull you down is becoming smaller and smaller. When you go above some height, right, then the Earth's pulling power, Earth's gravitational acceleration decreases, right? It is going by 1 over r. When you cross that limit, then you can escape from it, right? So those motion we will do in a moment. But yeah, so this is at certain height. Is this part clear? Is this part clear, guys?
Yes, sir.
Now let us say the third one, which is at certain depth. So when you go in the depth of when you dig the surface of the earth, and then you go beneath the surface of the earth, then what happens with this gravitational acceleration? So you have this earth, right, homogeneous earth, and then you are calculating at let's say this region you are calculating. So you are here. Okay, you are here. This is the M. Now you see that in this region, only this portion will contribute to the gravitational acceleration, right? Because only these region will pull this thing down, right? The rest of the region will not take part in gravitational acceleration. Only these regions will take part, right? So then we to calculate the gravitational force, we have to calculate this mass which is contributing. Okay, is that clear?
Yes,
Is
sir.
that yeah? So this is D, and this is R, right? And we have seen that the we know that rho is uniform, density is uniform, right? Which means that if we calculate this density at this surface, so that is the mass of the Earth, so at R, right? That would be how much? This is 4 by 3 pi R, right? And at a certain depth. So let's say we are calculating from here to here. This. So how much is this R? Let's say total mass is m. This is what we have to find. So how much is the mass which is contributing to this gravitational force? So what is the distance from here to here? What is the distance?
R minus D.
R minus d, right? So that is R minus d whole cube. So that would be the density. And we know that the density is uniform. So we can write that these things are equal. Right. So 4 by 3 pi, 4 by 3 pi cancel. And m prime, this part goes in here. So r minus d q me and then divided by. So this is the mass. This is the mass which will contribute to the gravitational force. Okay. So now let us calculate the gravitational force. We have this thing which is m prime. We have this m, small m. This distance is r minus d, right? So f would be how much? G m prime m divided by r minus d whole square. That is the force, right, guys?
Yes, sir.
So now let us put all the values, right? So we can put the value of m prime from here. So that would be r minus dq, mass of the earth, and rq and r minus d whole square. So this part and this cube will cancel. So, and we have this small m also. Then we have f, which is g m e m r minus d and then r cube. And this is equal to m and gt. So this is m r minus t divided by r cube. M will cancel. And again we'll do the same thing. So what we will do is that we'll take r common, and this would be 1 minus d by r divided by r cube. So r and this cancel, this is r square So GD is GM by R square 1 minus D by. So how much is this thing, guys? How much is this thing? Yes, that is again,
G.
yeah, that is gravitational acceleration on the surface. So this is the gravitational acceleration at a certain depth. So again we see that the acceleration due to gravity at a certain depth will decrease, right? So again, combining all these three, we see that the acceleration due to gravity is maximum at the surface. So at the surface, the gravitational acceleration is maximum. When we go above the surface and when we go beneath the surface, then the acceleration will decrease. Any confusion up until now?
No, sir.
Okay, so please note down these. Note down, and if you, in the meanwhile, if you guys get any doubts, so please ask.
Okay, sir.
So the idea is that the density is uniform, right?
Yes, sir. Yeah, whenever you guys want to scroll down the screen, please.
Done, sir.
Yes, Ran.
This was just to show you guys that how can we use this form, right? This is water, right? And in here, this is also.
Whenever you guys have put it down, yes, noted, guys.
Yes, sir.
Is this clear or should I zoom this one? Whenever you guys want me to scroll down, please. Yes, noted, guys. Please tell me whenever you guys have.
Yes, sir.
Yes, guys. Great.
Can you scroll?
Finished, sir.
When I'm asking, then you guys enter. You guys want me to scroll down. Like, this total mass is m, and this portion mass is m. Yes, guys. Okay.
No, sir. Writing.
Time I will wait and you guys will tell me whether you. Yes, noted.
Yes, sir.
Hi, you guys are live. You guys it now.
No, sir. Writing.
Answer.
Done. Akif, anybody have put it? Amna, please.
Yes, sir.
Yes, Akif, okay.
Yes, sir. Finish.
Okay, these are the two things, right? So acceleration due to gravity will decrease when we go above or below the surface, and the gravity would be maximum at the surface. That is the two things that we take from the equation. Now the next thing is very important, gravitation. When we were doing the work energy and power, right? And if you guys can tell me that, yes, if you guys remember, if you guys remember what was the gravitational potential energy at this certain height? So what was the gravitational potential energy of this object? What was the potential energy of this object at this height?
MGH.
mgh, right? So that was mgh. So now in this chapter, you will understand that, or in this topic, you'll understand that how do we get this mgh, right? So you guys will find out that this is the approximated value, right? But yeah, what is the actual value? Okay. So how do we get this result? And this you will understand in this topic. So first, let us uh, let us find out, or let us understand that what is the work. Do you guys remember what is the work? Yes. What is the work done?
Force under displacement.
Right. So if you apply some force and the body is displaced, right? So this would be, let's say, delta x or x. So this would be the work, and that is fx cos theta. Right? Now, if you have a variable force, work done by variable force was this, right? Let's say they are at 0 degree, right? So this was the work, right?
Yes, sir.
So then we have to find out. So in the case of the gravitational potential energy, or in the case of the work done by gravitational, so what will be the force that we will take? This force would be the force by Newton's gravity, right? Or force by gravity. So this is force by gravity. This would be the force that, right, guys?
Yes, sir.
And let's say if these are two objects, M1 and M2 distance separation is x, then gravitational force would be how much? That would be M1 M2 divided by x squared, right?
Yes, sir.
Okay, so similarly, how the potential energy is given, right? So the gravitational potential energy. This is defined as work done by the gravitational force, right? Because the work done by the gravitational force, right? Work done by gravitational force in bringing mass, let's say M, from infinity to a fixed point. Uh, okay, so this would be the gravitational potential, right? So this is the work done by the gravitational force in bringing a mass m from infinity to a fixed point down, right? So let's say that you have a mass m, it is at infinity, right? And it is brought by this gravitational force, and that is done by this mass of the earth, right? From, let's say, this point, from infinity to this point. So let's say this distance is x, right? And we are taking this x from, let's say, here to here. So this is some part. So what would be the gravitational force from here to here? Let's say this is mass is m. So what would be the gravitational force? Yes, guys, what would be the gravitational? From the center to this point, this is distance x, right?
Yes, sir.
So gravitational force would be G ME, M divided by x square, right? Right?
Yes, sir.
And yeah, so I should sorry. Yes, this is from let's say this distance is x, and I'm bringing from infinity to, let's say, this point, this uh, yes. What would be the work done? That would be F dx. And you see that what is the angle between force? So force is gravitational force, which is in this direction, right? Force is in
Yes, sir.
this direction, and I'm taking this mass from here to here. So displacement is again in the same direction, right? So F
Yes, sir.
and X have same direction. So then I can write F dot dx as F dx. So I can write this. And I can put this value of F, right? That is F G. That is F G dx. And I'm bringing from infinity to a fixed point. Then we have to just integrate this thing. That would be how much? So infinity to R G M E M divided by x squared. So G, M, E, M, these are all constants, right? So we can take it outside, and the integral is 1 over x square dx. So what is the integral of 1 by x square? What is the integration of 1 by
0.
x? 0. Integration of 1 by x square. I have written this so many times,
1
but
by x.
yeah, so nearly there. So xn plus 1 divided by n plus 1. This is the integral. N is how much? For this case, n is how much?
Minus 2.
Minus 2, right? So x minus 2 plus 1 divided by minus 2 plus 1. So this is x minus 1 minus 1. So that is minus 1 by x. Okay. So this would be GMP M infinity to R and minus integrated. This is minus 1 by x and infinity to R. So we can take this minus sign outside. So this is G M E M, and this is 1 by x, 1 by infinity n. So first we put the upper limit. That is 1 by r, and minus of this is 1 by. So what would be what is 1 by infinity, guys? What is 1 by a very large quantity? Okay, so you guys
0.
did 0. Yeah, so that is correct because 1 by 0 is infinity, right? So if we take this side and the other side, so 1 by infinity would be 0. That is 0. So we will have gravitational potential energy that would be minus G M E M divided by K. This is the gravitational potential. If we have two objects, two mass, M1, M2, right, and the separation is R, then the gravitational potential energy would simply be minus of G M1 M2 by, that is the gravitational potential energy. This minus sign signifies that the force is attract. Force is attraction. That is what it says. Is this thing clear? Right.
Yes, sir.
So,
Okay, so we still have not got our potential energy. This is not in the form of mgh. That we will see. But you guys, please note down.
Okay, sir.
Please. This is the pointer, right? After I have done this work, the potential energy, then only escape velocity, orbital velocity, and energy of the satellites. Only three topics will be remaining, and then this chapter. Okay, note it down, guys, and then in tomorrow's class, I will start this chapter, which is properties of solids, mechanical properties of solids. Whenever you guys want me to scroll down this screen, please tell me. Yes, whenever you guys want me to slow down, please tell me.
Answer.
Done.
Finish, sir.
Yeah. Whenever you guys have completed, please tell me.
Answer.
Oh, you have already completed. Everyone, yeah, whenever you guys have
Finish,
Yes,
sir.
completed.
I completed this.
So then, yeah, this always remember that this is the actual potential energy, right? This is how we write the potential energy. And how do we get the other one? So let's say that we are bringing some mass from, let's say, this B point, right? So let's say from this B point to this A point. This A point, which is the. So then what would be the change in potential energy, right? So change in potential energy, that would be in here, the potential energy is how much? That is minus GME M divided by RB. Okay. And in here, let's say the potential energy at A, that would be minus GME M divided by R. So change in potential energy would be how much? Change in potential energy. That would be delta U, which is UB minus UB, right? Which is minus GMEM divided by RB minus of minus GMEM divided by RA. So then this minus minus will cancel and I can write this in this side. So RA minus of GMEM divided by R. So I can take this GMEM common and this is RA minus 1 by R. So what did we learn in the work energy and power? So we talked about that at some certain height, right? We are taking the object from here to here, right? So we are taking the object from, let's say, what is RB? RB is, this is R and this is H. So this is R plus H. So we are taking an object from RB plus H to this RA, which is R, right? So at certain height, the object is at, let's say, we have this surface and this is certain height. So we are taking an object from here to here. So what is the change in potential energy from here to here? That is what we call MGH. Right, guys? That was the work done, right? In bringing from this mass to this mass. Is that,
Yes, sir.
yeah. So now let us calculate what would be the change in energy in this case. So if we put the value in here, so RA is R minus RB is R plus H. So this is, we can take LCM, that is R plus H minus R. This R cancel and we have GME and MH divided by, and R we can take common. So this is R square and 1 plus H by, right? So if this H is very small, H is very small than R, so then we can write 1 plus H by R as 1. Okay, then this would become 1 and you will get GME by R square and M and H. What is this value? What is
G.
this? So this is G, right? And this is M. So that is when you get MGH, right? So this is the potential energy you get when you pick an object from surface to this height. And remember, this condition is only applicable when your height is very smaller than this radius of the earth. That is when this is applicable. Otherwise, you have to use this one. This would be the potential energy. Is that clear, everyone?
Yes, sir.
Okay, so you guys please note down this part and then we will do one question and then we can. Please note down this. what did I do? I have calculated in change in potential energy from B to A point. Yeah, quickly you guys note it down and then you one question. So then this would be very clear to you guys. Yes, whenever you guys have noted it down, please tell me, because we have to complete one question. Whenever you guys have completed noting it down, please
Answer.
done. Okay. Good. What about you guys? Amna and Aki, what about
Finished,
you
sir.
guys? Finished. Okay, so what did we learn? That if we have two masses, right, this is M1, this is M2, and the separation is R, then potential energy would be how much? Minus Gm1 M2 by R. So that would be the potential. Remembering this thing, right? Let us do this one. if we do this problem, then this potential energy will be very much. Yeah. So this is the equation, right? We have a square of length L. We have a square of length L, and we have to find out. So these are kept, all these four masses are kept at the corners of this square and all have this same mass. Then this is the length L. So we have to find out what is the potential energy of this system. What is the potential energy of this system, right? So to have a potential energy, what do we require? We require two masses which are interacting, right? So to have, we have to calculate what is Q, right? So to calculate potential energy, we require how these two masses, whatever two masses are, they are interacting. This we have to figure out. So how many combinations of M1 and M2 would be there, guys? How many combination would be there? Let us pick this one. So for this one, this could interact with this one, right? This could interact with this one, and this could interact with this one, right? Clear?
Yes,
Yes,
sir.
sir.
So we have three combinations. Okay, let's say this is A, this is B, this is C, and this is D. So at A, we have three combinations. Now let us pick this one. So let us pick this guy. This one and this one we have counted, right? So one would be this one between these two, and the other would be this one, right?
Yes, sir.
Yes,
This,
sir.
so there would be two interactions from B, and then this one. So for this one we have counted this one, we have counted, this one we have not counted, right? So at C we will have one interaction. So we will have potential energy contribution due to 3 to 5 and 1, 6 contributions. Is this part clear?
Yes, sir.
Okay, so you guys note it down and then we'll discuss this question in the next class. So only the thing which is remaining is that we have to use this one. Q is minus GM1 M2 divided by R. So for all these M1 and M2, we have to write 3, 2, and 1, 6 contribution. So you guys note down this part and we will do this question in the next class. Okay.
Okay, sir.
Please note down this part and in the next class we'll talk about this. So tomorrow we will finish this chapter and start the next chapter. Whenever you guys have noted it down,
Done, sir.
okay, Akib and Amna, what about you guys?
Yes, sir. Finish.
Sure.
done. So yeah, see you guys tomorrow, and then we'll do this question. So in this question, there are two parts. One part is to calculate this potential energy. Second part is to calculate this potential. So that we will also learn. Bye guys. Allah Hafiz.
Bye, bye, sir.
And
Thank
see
you,
you
sir.
guys.
Allah